Okay, so how would you approach finding minimum sampling frequencies to prevent aliasing? What is a minimum sampling frequency to prevent aliasing?
The Nyquist rate, 2 times the maximum frequency.
That Nyquist rate, right. So how do we figure out what the frequencies are? We know that the Nyquist rate says you got to sample at least 2 times the max frequency in your continuous time waveform. What are these frequencies? Anything multiplied by the t is a type of omega measured in radians per second. And it's pretty clear if we call this omega sub 1, omega sub 2, omega sub 3, that omega sub 3 is the fastest frequency. So our first step is to convert that into a, when we talk about the Nyquist sample rate, the Nyquist sample rate is in samples per second. So we've got to convert this omega into a frequency. So the frequency, any frequency, is just equal to omega over 2 pi. So our first frequency here would be 6 pi over 2 pi equals 3 hertz, and so on. But we really only need to worry about the fastest frequency, so that would be F3, which is omega 3 over 2 pi, which would be 26 over 2 pi, which would be 26 pi, which would be just plain old 13. So what it's saying is that 13 hertz is the highest frequency in our signal. 13 hertz corresponds to that. So we need to sample at least at 2 times F max in our continuous time system, which would be 26 hertz. So we need a sample at 26 hertz, or in a different type of units, it's 26 samples every second. And if we do that, we've met the Nyquist rate, and we're not going to have aliasing in our signal. Questions about that one? So the next one's a little bit more complicated. It's find what our sampled waveform is if you sample it at 10 hertz. So Hayden, are we going to, does that meet the Nyquist rate, or are we going to have aliasing for that?
We're going to have aliasing.
Aliasing, right. We're going to have tons of it since 10 is a lot less than 26. So, bummer. Now, the general rule is that y of n is equal to, so here's our discrete time. It's equal to our continuous time, where we're going to sample it at time t is equal to n times t sub s, where t sub s is our sampling period. And our sampling period is just 1 over our sampling frequency. So if we are sampling at a sampling frequency of 10 hertz, we're sampling every 1/10 of a second. And that works out from seconds per sample. And that works out dimensionally too, right? If f of s is samples per second, you take 1 over that, you get seconds per sample. So every sample is 1/10 of a second. Samples are separated by 1/10 of a second. So let's figure this out. Our y of n then would be equal to our cosine of, every time we see a t, we're just going to replace it by nts. So copying this, we got 6 pi, and then we've got this t, and we'll replace this by n t sub s, where t sub s is 1/10, plus 2 cosine. From up on top, we've got 14 pi, and then n times 1/10. Minus 5 cosine, 26 pi, and 1/10. Okay. So we can simplify that a little bit. This is cosine of 0.6 pi n plus 2 of cosine of 1.4 pi n, and then this is minus 5 cosine of 2.6 pi n. Now you can read out your discrete frequencies. It's your discrete frequency in omega is whatever's multiplying, is whatever the n is multiplied by. I'm having problems with the pen widths here. So this would be our first discrete frequency, our second discrete frequency, and our third discrete frequency. And while this is correct, it does not keep all of our discrete frequencies between 0 and pi. So we're going to have to do some mathematical tricks here. The first one is between 0 and pi, so we don't need to change that. We do need to alter this, the second one and the third one. So we could write this equally well by, we want to somehow bring this down to within 0 to pi. So we could say this, 1.4 pi n minus multiples of 2 pi n. And we can kind of see when we do that, that'll bring this down to minus 0.6 pi n, which is getting there. Similarly, this guy, we can subtract off multiples of 2 pi n. We could have multiplied multiples of 2 pi n. We could have subtracted off 16 times pi n as long as it was a multiple of 2 pi, and 2 pi n certainly is.
So the second question.
Yeah.
Oh.
Go on.
So we can add, divide, subtract, and multiply by 2 pi. It's not just adding or subtracting.
You can add or subtract any multiple of 2 pi. There's no difference between saying 5 cosine of x plus 28 pi n. You can do that times 28 pi. That's okay. 28 pi n is okay. These are all multiples of 2 pi, and you can always add or subtract any multiple of 2 pi without changing anything.
Sir, you mentioned something about multiplying and adding that. I just got kind of confused by that.
So you can add any multiple of 2 pi n. So this is a multiple of 2 pi.
Thank you, sir.
Let me make this more clear. You can add or subtract any multiple of 360 degrees. And so what we're doing here is we're adding or subtracting a multiple of 360 degrees times n, where n is an integer, which is always okay. And that's what lets us do this operation.
But sir, if it's between 0 and pi, does that negative 0.6 still work?
Say that one more time.
If it has to be between 0 and pi, does that negative 0.6 pi?
It does not. It does not. So we're going to have to work on that a little bit more. So this is a work in progress here, but this certainly works. We've got now 0.6 pi n. So now, and for completeness sake, I'll write this over.
Should that be a minus 5?
0.6
Oh,
pi.
yeah. Thank you. You're right. You're exactly right. I lost that minus there someplace. Thank you. Okay. So now we're close. We've got everything except for this guy in our desired range. But cosine is an even function. And because cosine is an even function, we know that cosine of x is equal to cosine of minus x. Just a small aside out there. And so therefore, we can say this is equal to cosine of positive 0.6 pi n minus 5 cosine of 0.6 pi n. And now we've got all of these guys in that desired range of 0 to pi. And now we can go one step further and say, hey, these are actually all the same cosine. So we can just add 1 plus 2 is 3, minus 5 is 3 minus 5 is negative 2 cosine of 0.6 pi n. And so this would be the answer to the question.
Sir, quick question.
Shoot.
If the terms of this equation had different omegas, that's fine, right? As long as they fall between 0 and 2 pi. Okay.
Sure. It just so happened that they all turned out the same. But if you had something that looked like a cosine of 1.7 pi n, I would still subtract 2 pi. have to subtract 2 pi n. That would give me a cosine of minus 0.3 pi n. And since cosine is even, that's the same thing as cosine 0.3 pi n. And so this first thing is equal to the second thing, and the discrete time frequency is omega equals 0.3 pi. Does that answer your question?
Yes, sir. Thank you.
Great.
Yes, sir, I have a follow-up question.
Shoot.
So, well, I guess first question, could we expect or anticipate a sine function being somewhere in that y of t?
Okay, let's give that a shot. If you had a sine of 1.7 pi n, my first step would just be to say that's equal to cosine of 1.7 pi n minus pi over 2 radians. And so then just continue on with what we did up above. That would be equal to cosine of 1.7 pi n. We could subtract any multiple of 2 pi n. Still have to carry over that pi over 2 part. That will give us eventually minus 0.3 pi n minus pi over 2. And now we can use the fact that cosine of x is equal to cosine of minus x to say that's equal to cosine of positive 0.3 pi n plus pi over 2. Does that answer it?
Yes, sir, quite well.
Okay. Any others?